All right, so we pretty much look for, again, solubility and electrolyte properties. So we have two definitions of solubility. Do you recall the two definitions for solubility? One is qualitative, the other is quantitative. And so, what are the two definitions for solubility? Qualitatively, we have three categories: soluble, slightly soluble, and insoluble. But it's not black and white. The cutoff is around 0.1 moles per liter. If you can dissolve more than 0.1 moles per liter, we call it soluble. So if you can get a 0.1 molar solution or higher, soluble. If it's less than 0.1 molar, then it's insoluble. And around 0.1, we call it slightly soluble. And so that's the qualitative cutoff. Then we have quantitative solubilities. This qualitative, okay, it's soluble, but how soluble is it? And so how soluble it is, how much will dissolve is quantitative, and usually quantitative solubilities are given in different units. When you look at, where can I find solubility data? The handbooks. We have two very common handbooks. The CRC, have you heard of that? And unfortunately we don't have a copy out in the lab, but this is what it looks like here. The CRC Handbook of Chemistry and Physics. In here you can find lots of data, not just solubilities, but melting points, boiling points, a whole bunch of physical data, and some chemical properties as well, plus a lot of physics and math. The other handbook that's common in chemistry is this one.
How do you say that? Is that just Merck?
Merck Index. The Merck Index.
I can imagine someone's first name, but whose last name is Merck?
Well, you heard of the pharmaceutical company, Merck?
No.
That's a big pharmaceutical company.
Oh no.
And they publish this. Therefore, this is published by a pharmaceutical company, so obviously they're going to emphasize drugs and biologicals. Not so much inorganic. The CRC is much more heavily weighted in inorganic chemicals, and this is more weighted in chemicals, drugs, and biologicals would be mixtures, common biological mixtures, tinctures, whatever.
I feel like this is something my mother would know. She's a nurse.
Yeah, I'm sure she may be familiar with the Merck Index, but maybe they have something more specific, because this does have a lot of inorganics as well. But those cost money, and even the online, you can't look anything up unless you're a subscriber. And so Wikipedia, you have to be wary of sources like Wikipedia. But what I found for the chemical data is pretty good. And so if we go to, let's say, NaCl.
Or sodium chloride.
Yeah, or sodium chloride. Once, one semester in Chem 1A, I asked, on the final, what is the formula for sodium chloride? And do you know what I saw? SOCl. I couldn't, well, I had to rethink everything. Something went wrong. SOCl. But anyway, NaCl, that's good. You recognize that right off. That's kind of what I expect. But this data is usually pretty good. the properties, the formula, the molar mass. Here, I use Wikipedia a lot for molar masses because I get tired of calculating molar masses, especially for these big, in the homework, sometimes you have these gigantic molecules. They're a pain to calculate the molar mass, so I just look it up. Appearance, colorless. When you look at the single crystal, it's colorless. Otherwise, a lot of people will say it's white, but in reality, you can see right through it. The odor, density is about twice as heavy. Well, that's a lot of solid salts are about twice as heavy. Melting point's really high, 800.7 degrees C. It's hard to melt the stuff. Boiling point is close to 1500 degrees C. But here we have the solubility in water. And so this is quantitative. We know that sodium chloride, all sodium salts are soluble. Is that a law or is that a rule? All sodium salts are soluble. A law you would expect to have zero or very few violations of, right? So what would you say? Sodium salts are all soluble. Law or rule? Well, actually, yeah, there are a number of sodium salts that are insoluble, actually. So it's just a rule. Those are rules for solubility. Rules are less stringent than laws. And so, anyway, this is quantitative here. So if I had 1,000 grams of pure water at 25 degrees C, I could dissolve 360 grams in there. And so there are lots of different units that people use. This is grams per grams of water, 1,000 grams. This is grams per liter. Solubility of ammonia, solubility of methanol. Methanol, you could only get 14 grams, 14.9 grams, about 15 grams in a liter of methanol. So it's not that soluble, but still, it might be a little higher. But here, there's some clarification. Here you can see the original source references. The good thing about the CRC and the Merck is it's updated every year, so they make sure they have the latest data. Here, I'm not sure who updates this, and if it's the latest data. Correct.
Do you have a preference between CRC and Merck?
Both they're complementary, so there's not much overlap. And so both are worth getting. And in fact, I have a copy. I have a copy of both, the CRC and the Merck. I bought it. The CRC, I forgot how much it was, but I think you can buy it for about $200. Merck is maybe about the same.
You know what I think would be a good product, sir? A international index for things like the CRC or the Merck. Kind of a less, info packed, but more wide based. Something covering everything. Kind of like a dictionary.
They have the Chemical and Chemical Engineering Encyclopedia at the library. That has a lot of stuff, and it covers a lot of different things as well. So anyway, we do look at this for the properties, but is this going to tell us about the electrolyte properties? Do you guys recall electrolyte properties?
If we can, electrons can break off as electrolytes.
No, not quite that. Yeah, I don't see any electrolyte properties here. Maybe they tell us up here. No, they don't tell us. They expect us to know this kind of stuff. And you know that sodium chloride is a conductor. Good conductors we call what? Well, there are different: strong, weak, non. So sodium chloride is a strong electrolyte, which means it's a good conductor, which means what? It doesn't mean solubility and electrolyte properties are two separate things. So something could be insoluble, but the tiny bit that does dissolve breaks up into ions. This is what it means to be an electrolyte. So we could still call it a strong electrolyte. Now there are two definitions for electrolytes as well. In Chem 4 I only give one because it's too much probably to talk about two different definitions for electrolytes. The two definitions are: one, does it dissociate? If it dissociates completely, we call it a strong electrolyte. The other definition is for people who work with batteries and electrical devices. The people who work with batteries and electrical devices is this. If something isn't very soluble but dissociates completely, we call it a strong electrolyte because it dissociates completely, but its electrical conductivity is going to be very low. Electrical conductivity depends on, you know what electrical conductivity depends on? You know.
How well the ions, the electrons,
Are electronegative or not?
how well they flow through the material. Electrons flow through the material.
Well, how well they flow through the material, that's good. That's, we have a name for that. How well they flow through the material is called mobility. You know what symbol mobility gets? It gets this symbol mu. Mu is used for lots of different things. Micros uses mu. So there's a lot of overlap with these symbols because they start running out of symbols. And it's not always consistent what symbols people use. What else? How well they flow, and how many you have. You know, you could have ions that flow really nicely, but if you don't have enough of them, then you're going to have poor electrical conductivity. And so we call that the number N. It's pretty much just the moles of ions that you have. And the final thing that depends on this, so for example, you could have something that's highly soluble, like methanol. But does methanol conduct electricity? It's mobile because the methanol molecules in water can move around freely. But does it conduct electricity? It doesn't conduct electricity. Why?
It's molecular.
It's molecular. It doesn't break up into ions. It has no, what we call no charge. No charge. Each charge is given the symbol E. And electrical conductivity is given the symbol sigma. And so this is conductivity. Conductivity is inversely proportional to something that we call resistance. The conductivity, the unit for conductivity is Siemens, as in the semiconductor company, Siemens, S-I-E-M-E-N. It is. And this is inversely proportional. You don't need to know this. You don't need to know this equation. But this is inversely proportional to this big omega. You know what omega stands for? Ohms. And it's ohms is a measure of resistance. The resistance is it doesn't flow freely. If something doesn't flow freely, it's got limited mobility, therefore high resistance. So we have two definitions. You know, if you're working with, these are for, this is for, you know, we have two types of conductors. We have electronic conductors. Electronic conductors are like metals. The electrons conduct the electricity in metals. They have to be mobile. You know, electrons will have a negative charge, they're mobile. We got lots of them in metals that can move. Mobility. And then we have things called ionic conductors. So copper is usually the standard for electrical conductivity. You know, copper has excellent electrical conductivity. So if it conducts as well as copper, then you say it has good metallic conductivity. And so you could have salt solutions that conduct just as well as copper metal, like sodium chloride. You know, sodium chloride aqueous conducts very well Because what happens is it's pretty soluble, 360 grams, and that you can dissolve in 1,000 grams of water. And then what happens when the sodium chloride dissolves? It breaks up into ions, and those ions are quite mobile. And so, how about solid sodium chloride? Would you expect solid sodium chloride to be very conductive?
No,
Why not?
because it's a molecule, it doesn't break down.
Okay, well, we have to, this, we have to be careful what we call molecules, because molecules for chemists are very strictly defined. A molecule, how would you define a molecule in chemistry?
A combination of elements.
Yeah, it's not just a combination, but it has to fulfill some additional. So it is a combination of elements, or it could be just one element, like nitrogen, N2, or hydrogen, single element. But the constraint of a molecule is it has to be covalently bonded, typically, and it has to be a it doesn't have to be organic. Like, for example, CO2 is considered inorganic, not organic. It has to form not a lattice. We don't want it to form a lattice. It could form a lattice of molecules. It has to form discrete units. That is, it has to form well-defined discrete units. Where's this? Is this a molecule of sodium chloride? And then we could have one molecule, 2 molecules, 3 molecules, and each of these would be like these little crystals that we put together. No, is there a beginning and an end? Can you have, in other words, can you have any size sodium chloride crystal from tiny to big? Yeah. And so there's no discrete, isn't this a molecule here? If I pick this purple one and this green one here, isn't that a discrete molecule of sodium chloride? Which one is sodium, which one's chloride? Purple, sodium or chloride? Should be. The purple one, sodium or chloride? Sodium. Sodium's correct. The green one? Chloride. This is opposite of what you'd expect from the periodic table. Sodium, the element, versus chlorine, the element. Which one's bigger? Sodium's bigger than chlorine. But when you create ions, then the chlorine size doubles and the sodium size contracts in half. And so when we have cations in general are smaller. In fact, this is a rule, this is not a law, but cations are smaller than anions. There are only like 2 or 3 exceptions. But cations are smaller than anions. Anyway, is this a molecule of sodium chloride, this purple one and this green one? No, because, why am I picking this green one? Why don't I pick this green one here, or this green one, or this green one here? You see there's no distinction there. These are ionic bonds. Ionic bonds, if you have a positive, what do you want to surround yourself with? As many negatives as possible. And so if you're positive, you want as many green ones as you can fit around you. Well, in this case, for sodium chloride, it can fit actually 6 if you look inside there. This is on the surface. This is the edge. Edges, and the most susceptible to attack is when you start dissolving this, the corners dissolve first, because those are going to be the most loosely held. Because this purple is only held by these 3 greens, whereas the edge, this purple is held by not just these 4 here that you can see, but there's going to be a 5th one inside here. And so this is going to be harder to attack if you're water. Water is going to try to pluck these ions off. And so the corners get attacked first, then the edges, and then the face ones are going to be harder to remove. Does that make sense? And so when you dissolve a sugar cube, what dissolves first? The corners dissolve first, because they're going to be the least. But anyway, it just ends here, but we can build a bigger crystal, or we can build a smaller. So therefore, we want to know, what is the smallest unit of sodium chloride that we can have? The smallest unit of sodium chloride that we can have is 1 sodium ion and 1 chloride. And so if we take just one sodium and one chloride, what do we call that? Do we call that a crystal of sodium chloride? No. Do we call it a molecule of sodium chloride? No. We call it a formula unit of sodium chloride. So the smallest unit of sodium chloride is the formula unit here. And that would be it. So we're going to be looking at electrolyte and solubility for part 1 of today's lab.
In your conductivity equation on the board, was the mu representative of solubility?
No.
What would that represent again?
Mu represents mobility. N is representative of solubility. N is going to be big for soluble species, small for insoluble species. And so this is the number. What we call these are the number of carriers. So the carriers could be ions or electrons, whatever. The E is the charge. This doesn't have to be electrons. This is just charge. Since I'm kind of, well, actually, I guess we're okay. Let's go with this. So let's take a look at what we're looking for first. Number 1, what are we going to test?
Distilled water.
Yeah, distilled water. And we're going to test it with this. This is our electrical conductivity apparatus here. You've probably seen this before, right? And so we have a copper. This piece of copper here we call an electrode, and so we have 2 copper electrodes here. And basically, we're going to plug this in and then see if we get any electrons to flow here. And nothing's happening. It's not lit up because we call this an open circuit. An open circuit means that there isn't a continuous path for the electrons to travel. And so the open is this gap here. We could close this circuit by just getting something that conducts electricity. Here, I can try to close this circuit here. Oh, I don't want to. I don't want to electrocute myself. But we could use a piece of metal. I had a piece of metal with a.
But it's so fun to feel my hand go numb after it absorbed.
Oh, I got something. Here. This. You know what this is?
The graphite rod.
Graphite rod. Let's see if a graphite rod conducts electricity. Ready?
Right.
Yeah?
Oh, I see.
Okay, so the graphite rod conducts electricity pretty well. Also called pencil lead.
Isn't that really used in microwaves?
I don't actually, maybe, but not for conducting electricity. Maybe for microwave waveguides. Okay, so I can close the circuit like that. It looks like these electrodes are quite dirty here, so probably need to clean it. And then, did I forget my goggles? Well, anyway, what do you think? Distilled water, is it going to conduct electricity or not? No. Oops.
If you have perfectly ionized water, you can drop it down the phone and it won't electrocute, it won't break.
Yeah. Distilled water, we used to test our distilled water. Do you know how we tested our distilled water? We had an ohm meter, and we measured the electrical resistance of our distilled water. And if it was reading mega ohms, then it was good. But when you saw the electrical conductivity go up, then you knew it was bad. The water was no longer a good insulator. Distilled water should be a good insulator. Not tap water, though. I don't know why I don't have any distilled water here. Here it is. Okay, it looks like the budget, we didn't have the budget for distilled water, so you know what we're going to use? We're going to use DI water. The first thing is I need to clean these electrodes here. They're so dirty. Do you see the salts on here?
Yeah.
Some salts on there. So let me try to get rid of some of those salts here. I'll just do the water without the goggles and the salt solutions, like sodium chloride. Should be all right. Hopefully this is just sodium chloride
Give it a nice
or potassium. It's probably potassium chlorate. But that should be all right. You know, I'm going to contaminate my DI water here. Maybe it's already contaminated. I don't know. They probably put some fresh DI water in here. In fact, you know, I don't want to. Let me just try it with this DI water first. All right, what's going to happen?
It's not.
Not plugged in. Nothing's going to happen.
Non-conductor.
Okay. Yeah, it's a non-conductor. Are there ions present in water? You might have learned this in Chem 4, or maybe not. Do you know about autoionization of water? You know what gives water its pH? What is the water pure? I mean, what is the pH of pure water?
a little over 7.
Not a little over 7.
It is.
7. Yeah.
All my water is just
Oh, yeah. If it's over 7, is it acidic or basic?
basic.
It's basic. A lot of people like basic water. You know, it has a smoother taste, like soap, slippery, you know. Yeah, soaps are very basic. Well, what happens is, you know, this is water at 25 degrees C. When you have water at 25 degrees C, you know, temperature is, you know that temperature is directly proportional to something, energy. What kind of energy is it directly proportional to? Temperature. Like, for example, if we're at 0 Kelvin, what's happening? No kinetic movement, no motion. You know, kinetic energy is the energy of motion. So if we go from 0 Kelvin to 298 Kelvin, 25 degrees C, there's going to be a lot of motion. Right? And so this is water at 25 degrees C. I don't know if it's 25 degrees C in this room. I think it's lower, but we just use 25 degrees C because 25 degrees C is a convenient temperature that we pick as standard temperature. Is 25 degrees C standard temperature? No. 25 degrees C we call room temperature. So at room temperature, there's a lot of kinetic energy. And well, what does that mean for water? For water, we know there are 3 types of motion. What are the 3 types of motion for water molecules?
Rotation.
Yeah, the water molecules can rotate. This is what microwave ovens do. Microwave ovens are tuned to the rotational frequency of water so that when you hit it with microwaves, it rotates it and causes collisions and things get hot with the motion. And so microwaves are very efficient because they're tuned to that. So rotational, water molecules can rotate. And then what else? Actually, have you seen water molecules rotate?
It's like when you get a good spin on a soccer ball, just spins up space.
Yeah, it doesn't move fast.
You know what ab initio means? Liquid water ab initio molecular dynamics.
What is that issue?
Ab initio means purely from theory. This is just a theoretical calculation. And so ab initio just means mathematical simulation of water using the theory of chemistry. What is the theory of chemistry? Quantum mechanics. So these are quantum mechanical calculations. But to do these calculations are very difficult. So what they do is they use a lot of approximations. Approximations are simplifications to make the math easier. Otherwise they can't do this. The math is too horrendous. So these are
Society sources. Details matter. Introducing Grammarly citations features.
do my YouTube videos have ads?
Yes.
Yes, YouTube has ads.
It has ads. I didn't monetize. For a reason, I thought they wouldn't have ads.
Now,
But
they introduced a new policy, I believe, a year and a half back, where they monetize, where they show ads on videos that even don't have monetization turned on.
yeah, all right. Yeah, I didn't monetize them because I didn't want ads. But apparently they put ads on there.
It's only starting ads. You don't get ads during the video now. You only
Okay,
get
that's
ads during
good.
the start and ending.
It's pretty limited when I'm trying to look up how to do CPR.
Well, anyway, this is what a molecule is. A molecule should be a discrete unit. A discrete, in this case, we have a discrete molecule here and here. Versus what we saw earlier. What we saw earlier was an ionic lattice, which doesn't have a discrete unit. We have other lattices as well that don't have discrete units, but this does. Even in ice forms a lattice, but it's a lattice of discrete molecules. What are these purple lines representing? Intermolecular forces. So this is what causes them to be sticky. Water molecules are sticky because of these intermolecular forces holding them together. The primary intermolecular force you would expect in water is the hydrogen bonds. So this is primarily hydrogen bonding interactions. In terms of energy, the weakest covalent bond is around 100, maybe a little less than 100 kilojoules per mole. And hydrogen bonds are around 25 kilojoules per mole. So it's about 1/4 the strength of the weakest covalent bond. The weakest covalent bonds have to be protected from light because they'll break when exposed to just visible light. So usually we store those in amber or black bottles, so they don't break apart like iodine. Iodine has very weak bonds. Hydrogen peroxide, if you put your hydrogen peroxide in a colorless bottle, it wouldn't last very long. Visible light will break apart peroxide. Well, in addition to rotations, can you see some rotations?
Yeah.
What other types of motion are there?
Kind of back.
Translational, it just moves. It can move anywhere, but it's kind of slow. It's called diffusion. It's kind of slow because it gets stuck, in this field of water molecules. So it's like this is a. I heard an interesting analogy the other day. If this is like a big event, you know, moving from one side to the other can be slow, especially if they're all your friends. And the water molecules are all friends of one another, and so it takes time. Well, anyway, so we have translational, rotational, and vibrational. And sometimes you can see it vibrating like this one here, and then the bonds. Do you see the bonds kind of vibrating like this? We've got vibrational motion. So those are the three types of motion that we have.
In
Did you
molecular
notice that?
dynamics, atoms are typically represented as single point masses inside random.
Were all the water molecules moving at the same energy? Now that's tricky because it looked like all the water molecules kind of had the same energy, but do they all have the same energy?
No.
No, they don't have the same energy. In fact, what do we have? They aren't all moving at exactly the same speed with exactly the same vibrations and exactly the same rotations. Instead, what we have is not the exact same energy, even though all, you know, that whole sample's at 25 degrees C. What do we have instead? We have a net. That net is the net energy is what we call the average kinetic energy. So if we look at the average kinetic energy, that's the temperature. Temperature is equal to the average kinetic energy. Well, plus some constant. But temperature is directly proportional to what we call the E sub k. Our book uses this symbol for kinetic energy. It's not the same E. Again, there's a lot of overlap with symbols, and so you have to keep track of them. This is the kinetic energy. And to indicate that it's the average kinetic energy, we write a bar over it. And so that's the average. And so at 25 degrees C, the net is this average here. Okay, let's see, there. That average is an average of what? Of all the molecules together. And usually when we try to visualize all the energies of all the water molecules, you know, there's slow ones, there's fast ones. How do we visualize that? Uh-huh.
A way you can visualize that is like traffic, right? You have some cars zooming past others while some drive at a constant pace, right?
Yeah.
So every car is moving at a different speed, stopping and slowing.
Yeah. So do you measure those individually? Okay, I'm going to follow this car for a while and then that car. Or can you see the whole thing at once? Is there a way to visualize everything at one time? You know, or do you have to pick one and just watch it?
You can visualize everything at once.
Yeah, we try to visualize everything at once, and we visualize it using what? Usually in science we like to, you know, when we take observations, we can take lots of individual observations, but then we try to look for what? And this is a scientific method. We take observations and we look for patterns and trends. And usually when we look for patterns and trends, we try to do it by making, this is very common in science, we like to make graphs. Right? And so what would the graph look like for the kinetic energies of water?
Topography. How do you topography?
It's like linear and then it stops or it intersects absolute zero. It'll stop it.
Well, not the temperature. It's going to be a fixed temperature. The temperature is still 25 degrees C. And so the temperature is fixed at 25 degrees C. This is water. And we know that there are going to be some slow movers and some fast movers, and we want to just picture the whole thing at once. And this is very famous. Has a name. Two last names. Maxwell Boltzmann. Are you guys familiar with the Maxwell Boltzmann thermal distribution? what does it, it's not a bell-shaped curve. What does it look like? And so what it looks like is this. This is the population or the number. And this is going to be the kinetic energy here. So there's some slow movers and some fast movers. Does somebody recall what it looks like? No? You can't visualize it?
Let's say it looks like a parabola, but for our case, we would probably use a scatter graph.
No, we're not going to use a scatter. This is going to be a line. I don't, it's going to be based on a lot of experimental data. But it kind of looks like a bell-shaped curve with a high energy tail. This is, I don't know, can't recall how many times it's shown in the others, but not everybody calls it Maxwell Boltzmann. Actually, let's take a look. Here. We call it a distribution. These are some common images, so you can see it's a bell-shaped curve with a higher energy tail. This is what happens when you change the temperature. Let's say the green were room temperature, 25 degrees C. What happens is if you cool it, then the average goes down. The average is what we call a root mean square average right here. It's on the shoulder because of this tail here. But if you cool it down, then the whole population shifts to lower energy. And so this would be it. The peak height increases because the area has to stay constant because the population is constant. We aren't adding more into the population and we aren't removing. Likewise, if we heat it up, the whole population shifts up in energy and the average shifts up. The average would be up here now. But this is the Maxwell-Boltzmann distribution. You can see that there's a very, very small population of very high energy molecules. Do you see that here? This population, in terms of water, there's a cutoff here. We're going to call this cutoff this dashed line here. If we're beyond the cutoff, what that means is that these water molecules are actually quite violent. I mean, in terms of kinetic energy. That is, if you look at that population, most of the population is just cruising around like this, but 4 out of a billion are going to be like really moving. And that really moving, they can have a violent collision. And so all of a sudden there's a violent collision. That violent collision results in what we call water autoionization. So this is water at 25 degrees C. And you don't, well, you should know Maxwell-Boltzmann because this is a very famous distribution. You're going to see this like 5 or 6 times in this book, and maybe in intro you'll see it a number of times as well. We call it Maxwell-Boltzmann distribution, or temperature distribution, or thermal distribution. This is thermal distribution of what you'd expect in terms of kinetic energy. This is important because these high energy things can do certain things. And so we'll have some cutoff up here. And so that high energy thing, what it can do is this. If I have one of these that's moving quite violently, this one here, they can collide. And in this collision, it's so powerful it breaks bonds. And we end up breaking a hydrogen off this and giving it to the other. And so we end up forming hydronium and hydroxide. In pure water, the hydronium is 1.0 times 10 to the minus 7 molar. And the hydroxide is 1.0 times 10 to the minus 7 molar. And we call this pH 7.00. pH stands for the power of the hydrogen ion concentration. The power is 7 here. We're allowed 2 sig figs. And power functions are logarithmic functions, like the Richter scale. And so this would be 7. It goes by orders of magnitude. Well, 10 to the minus 7 molar isn't enough. Is there charge? Yes, there's charge. Do hydronium and hydroxide ions have mobility in water? These are aqueous. Sometimes I don't write aqueous, but I'll make sure to write liquid, solid, and gas. I just don't write aqueous because we do so many aqueous things that you just assume it's aqueous unless otherwise written. So we have this violent collision. It generates 1 times 10 to the minus 7 molar, or 0.1 micromolar, hydronium and hydroxide. Hydronium is mobile. Water is mobile. Right. Let's go back to the conductivity equation. Conductivity is equal to, what is it equal to again?
It's N mu E.
N mu E. N mu E. Fortunately, this is a pretty easy equation to remember, but you don't have to know this equation at all. I had to learn this equation when I was taking took a materials science course. N is
The number.
so in pure water. Is there a high population of water molecules?
Yeah.
Yeah, high population of water molecules. Mu is
The mobility.
are the water molecules mobile?
Yes.
Yes. I mean they're sticky, but they're mobile,
They're
right?
moving around.
They're moving around. Actually, that was slowed down. That was not real time. That was really, really. I think was the time bar on that?
What's that? It was like mid 20.
No.
Oh.
Not that time. Not the YouTube time bar.
No, then.
No. Shoot.
I was like, when I imagine water vibrating, I imagine it either like TV static or like a paint shaker.
Sometimes they'll show the time bar here, and it's like in like nanoseconds, because they really have to slow it down so you can see it. This is ultra slow motion. But that's okay. Here, let me see if they tell us how much time that was.
10 was it picoseconds?
Where does it say?
The shunt trajectory
It says
corresponds
in
to
the description.
10 ps.
Oh, okay, thank you. 10 picoseconds in 1 minute. It's slow. I mean, pico, I was thinking nano. That's pico. That's what happens in a picosecond. Which, pico's 1 trillion? 10 to the minus 12?
Yes.
Yeah. So this is really moving. Thanks. So, it's got mobility. What's it missing? Charge. Right. But we know all water molecules aren't equal, and that some of these are going to have enough energy to actually react. This is a chemical reaction. This is what we call an acid-base reaction. This is what we call a Bronsted-Lowry acid-base reaction, or just plain old Bronsted reaction. In a Bronsted reaction, what happens? The acid, a Bronsted acid does what? This is why, Chem 1A is kind of a lot of repeat of Chem 4, because, how much do you remember? And so this repetition is always good, but it's also good to do repetition on your own, to review and repeat the stuff. But anyway, a Bronsted acid is a proton donor. A Bronsted base is a proton acceptor. So which water molecule is a proton donor? The left one or the right one?
Left one.
The left one here.
The right.
The right one here? Yeah, the right one here. That's different than Lewis. Although Lewis acids and bases aren't really talked much in Chem 4 or intro. Lewis acid, what is a Lewis acid? What is a Lewis base? Yeah, electron pair donor and electron pair acceptor. For Lewis acid base, we like to draw Lewis structures, and we like to visualize this. We like to visualize electrons moving. So for example, here, do you see this lone pair? This lone pair gets pushed into this hydrogen here. We're going to talk about orbitals in this. But what happens is, that's too many electrons for hydrogen. Hydrogen only wants how many electrons to complete its octet? Actually, hydrogen doesn't form an octet. Hydrogen forms what we call a duet, right? And then it'll be like helium. And so it only needs 2. But if these electrons get pushed into hydrogen, then it's got 4. 4 is too many.
Hydrogen and helium only wants to have a duet, right?
Yeah, only wants a duet. And so this is too many. What's going to happen is either it's got to go back, or this is what can happen. These electrons get pushed in, and then these electrons get kicked off. And so what we end up with is this. We end up with hydronium and hydroxide. Now, there are different ways of counting electrons. When we use oxidation state, do you know what we assume when we count electrons via oxidation state? We assume that the bonds are 100%. Did I do oxidation state for acetic acid? I think I did. Yeah. We assume that winner takes all. When winner takes all, that's assuming that the bonds are 100% ionic. Ionic. In formal charge, we do a different assumption. The oxidation state of oxygen is the same in all these. The oxidation state, winner takes all. And so when we look at it, winner takes all. It doesn't matter if it's water, hydronium, or hydroxide. They're all going to have the same oxidation state. What is the oxidation state of oxygen in these 3 species? Well, that's the number of electrons it has, but normally it has how many electrons? 6. So normally it has 6. It has 8 in all 3 of these, which means it has a -2 charge from having 2 extra electrons. Does that make sense? Yeah? Or no? So using oxidation states doesn't really give us much insight. It tells us about redox, but acid-base reactions are not redox reactions. What types of reactions do we have? This is what we're going to get into in this experiment and in these chapters. In fact, in particular this chapter. It depends on how you want to classify the reactions. There are different classification schemes for chemical reactions, but if you think about all the chemical reactions that occur in the universe, or just your body, can you count the number of chemical reactions that are happening inside your body right now? I mean, this is huge number of chemical reactions happening. So do you want to study those individually, or maybe classify them in categories of reactions? Yeah, we'll probably classify them. And so what we're going to do is we're going to come up with a simple classification scheme for chemical reactions. Do you guys remember how many types of chemical reactions did you learn in Chem 4 or Intro Chem or whatever Chem you took? How many different kinds of chemical reactions are there? Did you say 9? More than 9? 100? I mean, tell me, how many, if somebody asks, these are chemical properties. The physical properties we get from the CRC, the Merck Index, Wikipedia. The chemical properties, a little bit from those. But if we think about the chemical properties, how many different types of chemical properties are there in nature, in the universe, do you say? A lot, but we're going to classify it into certain number of basic types of chemical reactions. And do you remember how many basic? Did you have to memorize these? In Chem 4, you're supposed to memorize. Actually, the Chem 4 department, we're supposed to teach 7, I think, types of chemical reactions. Combination, decomposition, precipitation, neutralization, combustion. That's 5. 2 more. 2 more. Do you guys remember? You're actually supposed to memorize this. This is part of our course outline. You're supposed to memorize these, but I don't. That's too many different types of chemical reactions. So I do it a little simpler, I think, because how many of you memorized it? Nobody's memorized it, and so it's not. Maybe it's too hard to memorize that. This came up. This is why I've been thinking about this for quite some time, because when I was a student, a graduate student at UCSB, you know, I was a teaching assistant too, and so one of the students came up to me and asked me, "How do you predict chemical reactions?" You know, they couldn't figure it out by reading the book. And I thought about it, and I thought, yeah, that student's right. You can't really figure it out by reading the book because of the way it's organized. And so I came up with a simpler scheme for organizing chemical reactions. Actually, I didn't come up with it. It was taught in the higher level class. And so I just started using it for general chemistry. And so I break down chemical reactions into 3 basic types. Actually, do you guys recall the 3 basic types of chemical reactions? Metathesis. Single replacement is part of another type of reaction. Double replacement is what I call metathesis. I don't call it double replacement because not all metathesis reactions follow the AB plus CD double replacement format. And so essentially metathesis is double replacement, but you have more flexibility because, you know, if you have a reaction like this, silver ions plus chloride ions, what forms? Do you know what forms?
AgCl.
AgCl. It's a precipitate. This is double replacement, but does it fit the AB plus CD pattern? No. And so this is more flexible. If we call it metathesis, then it's a bit easier because we look for different things, not AB plus CD. If you only look for AB plus CD, then you're going to miss a bunch of stuff. So even though metathesis has this fancy name to it, it's not fancy. It's just what we call favorable ion combinations. And so there's metathesis, there's what?
Synthesis.
Well,
Actually,
all these are synthesis reactions. Synthesis just means you're making something new. In fact, that's what I like about chemistry. You know, I like about chemistry is you can make new things. You have that option of synthesis versus other things. You know, like geology. Geology, you could study things, but you don't really make things, new things.
that's why I like engineering. You need to make things.
Yeah, engineering too. Engineering, you can make things, so that's fun to make things.
Combination, decomposition, combustion, neutralization, redox, double displacement, synthesis.
Yeah, that's.
After
Did you get 7 of them?
Yeah.
So what were they again? Combination,
decomposition, combustion,
neutralization,
redox, double displacement, synthesis,
single replacement.
single replacement.
Yeah, synthesis is, all those are synthesis reactions, so single replacement. There you go, those are the 7. Now predict, you know, based on those. Well, you can predict as long as they fit that pattern, but sometimes they don't fit that pattern. And so what we have is metathesis, and then single replacement is thrown into a category called redox. Oxidation reduction is what redox stands for. And we're going to have single replacement, etc. in this. But we don't just have single replacement, we have a whole bunch of other redox reactions. like combustion. Combustion is a redox reaction. So I should just say single replacement combustion, etc. And we have one other type of reaction, and that is
Acid.
acid-base. In acid-base, we have two types of acid-base reactions. We have the Bronsted. In Bronsted, we look as a proton donor. And so if we're to visualize this reaction occurring as Bronsted, then this hydrogen is donated to this, and therefore this is the acid. And so we often see somebody circle the hydrogen and move it over here. But this is a different representation. This is Lewis. For Lewis, we look at the electron pair. We don't look at the hydrogen, and we look at where the electron pair can go. So this is typically the way things are done with Lewis, because Bronsted, what's more comprehensive, Bronsted or Lewis definition of an acid base? Lewis is much more comprehensive definition. And therefore, we can look at everything in terms of Lewis. We can't look at everything in terms of Bronsted. So we have this acid-base reaction occur here to a small extent. This is in pure water. So when you drink pure water, are you drinking hydronium? Yes. When you drink pure water, you're drinking hydronium. Are you drinking hydroxide? Why doesn't it kill you? If you're drinking hydronium and hydroxide, strong acid and strong base, why doesn't it kill you? Such a small amount. You know? And so when people ask, will I drink the hydrochloric acid? You drink it every day. But you drink it in such a small concentration that, if you drink tap water, you know, it's such a small concentration that it's not going to kill you. Now, would you drink 6 molar hydrochloric acid? No, definitely not. And so here, this equates to 4 parts per billion. This is not by mass, this is by molecule. So about 1 billion water molecules, I get about 4 of them reacting like this. Does that make sense? And so, but is that enough to conduct electricity? No, it's not enough. Did you see the resistance? Yes, maybe a tiny bit, but so small we got to go, what's beyond mega ohm resistant? If it's not mega ohm, then what's after mega? Giga ohm. Maybe
I would go tera.
Tera ohm. Yeah. But you buy an ohm meter. An ohm meter doesn't go down to giga ohms. I mean, go high. You know, it's not infinite. You know, but it's so small, it's not going to conduct electricity. So, in terms of this, we have mobility, yes. We have charge, yes. What are you missing? The number. And so this is why distilled water is thought of as an insulator, because it really doesn't conduct. We have the number so small. Yes, there are some, but it's so small. It is good that it's small, otherwise you'd be dead, right? If this number were high, you wouldn't be around.
Man, there's another way.
What? Yeah. Although they neutralize each other. This is called an equilibrium. And what we have in water is we have a dynamic equilibrium. In this dynamic equilibrium, there are different ways of visualizing this dynamic equilibrium. It's like most of the population's down here at the low end, hanging out here. This is energy on the Y, just some qualitative energy scale. But, you know, out of this billion water molecules, how many can climb the hill to create this? Because hydronium hydroxide are what we call high potential energy, you know, because this is at 25 degrees C, and these are at 25 degrees C. And so if they're both at the same temperature, the hydronium and the hydroxide and the water are at the same temperature, then they both must have the same kinetic energy. They have this, in fact they do, they have the same kinetic energy. And so the water down here, let's say the billion waters down here, have the same kinetic energy as the hydronium and the hydroxide way up here. What's different? Well, when we look at the energy, you know, the total energy of anything is equal to the sum of its plus this. The total energy of this water is equal to the sum of its the total energy will equal its volume depending on the amount. So the more water we have, the higher the total energy will be. But if we just fix the volume here, then the total energy is equal to the sum of its, well, mass and volume are proportional to each other. So the mass and volume that's extensive, and that would be it. But the total energy is equal to, this is why thermodynamics, have you heard of thermodynamics?
Yes.
Thermodynamics ends up being in the university, ends up being a weeder course. A lot of people end up failing thermodynamics. You know why? Because they get all the definitions all mixed up. You know, the total energy is equal to, and if you can't tell me like that, then thermodynamics is going to be hard, because thermodynamics deals only with energy. How are you gonna pass it when you can't tell me what the total energy is? Okay? And so that's why a lot of people struggle in thermodynamics. And so I'm going to spend a little bit of time. We haven't hit thermodynamics just yet, but we want to talk about some of these things conceptually now and then repeat it again. So hopefully by then you'll remember it. You know, because hopefully you'll read it over and over again, so it'll be easy to remember. So the total energy is equal to the sum of its kinetic energy plus potential energy. And so the total energy, you learned this in physics. If you had physics then. And so the difference here is the potential energy. And hydronium and hydroxide are very reactive. They'll kill you, whereas water won't. And so these are very reactive, and just 4 out of the billion can make it up here. So this is one way of visualizing it. But these are so reactive, they're going to fall back down. But a little bit, you know, as these fall back down, hydronium and hydroxide react reversibly to form 2 waters. Then nothing's stopping these from moving, so there's going to be another collision, and this is going to be replenished. And so what we have is something called a dynamic equilibrium. In a dynamic equilibrium, we have a fixed quantity here. It's pH 7. The pH is not changing. But the hydronium is changing, you know, because these are reacting, falling back down here, and new ones are coming up to replace it. And so we reach this state where we reach this state. So for every 4 that fall back down, 4 rise back up. Does that make sense? And so this is our dynamic equilibrium. Our dynamic equilibrium we can show in different ways. A lot of people show this as a big arrow backwards and a small arrow forwards, because this is heavily favored to this side. You know? But the rates are equal. So if 4 go up, 4 go down. And so these unequal arrows just show which side's favored, which side's the lower energy side. In this case, the reactants here. So even though pure water does have some ions, it's not enough to conduct any electricity like this. And so that was our DI water. Let's check our tap water. And so I'm going to dump this and put some fresh tap water in here. What do you think about tap water? It will conduct.
Slappy?
Yeah, it conducts. This is enough to easily kill you. Even though the light bulbs look dim and you go, ah, that's no big deal. Are you going to put any electrical appliances? Would you put this next to your bathtub? No. It doesn't look like much, but this is plenty enough to kill you because of the current. You know. But it's not the strongest conductor, because And so it's weak. Is it weak because it's a weak conductor? But what do you think is in here?
don't know.
Salts. What do you think the biggest salts are?
Oh,
Like I would say the biggest ones would be like sodium and
I would say iron from the pipes.
iron from the pipes, yeah,
Rust.
and
Lead. Copper.
well, maybe some copper. The iron ions are more reactive, and so iron is pretty low. Sodium's probably pretty high. And what do you think the most common anion found in tap water is?
Oxygen.
Oxide's pretty reactive. What do you think most?
Do you think nickel is?
I'm sorry,
Do you
nickel?
think nickel is? Nickel?
Nickel? Nickel would be rare, I think. Nickel, you know, things like copper or copper ions, these are metathesis type reactions. And so if you know some metathesis chemistry, the first level, you know, you have positive cations and you have negative anions. And so the higher the charge and the smaller the ion, the more reactive those are. And so we can look at metathesis reactions from purely electrostatic point of view. Electrostatic is just a word meaning you look at it from Coulomb's law perspective. Do you guys remember, did you cover Coulomb's law? Probably not. This is Coulomb's law simplified. Coulomb's law, now we have another symbol for charge. Two common symbols for charge are lowercase e and z. Z is the charge on A, and Z is also the charge on B, so we have a ZA and a ZB, two things. If they're the same charge, it's a repulsion. If they're opposite charge, it's an attraction. D is the distance between the centers of the charge. This is Coulomb's law. And so in other words, the smaller the species, ion in this case, the shorter the distance. The bigger the species, the higher the distance. So we look at the size. We're always interested in the size. But we also look at the charge. So for example, if I have a positive charge on this ion and a positive charge on this ion, which ion is going to be more reactive? The left one or the right one? The smaller one. And therefore, in Coulomb's law in chemistry, we look at the charge density. How concentrated is the charge? If the charge is more concentrated, then it's got a higher charge density, meaning it's going to be more reactive. If it's got a bigger size, it's going to have a lower charge density. It's going to be less reactive. So metathesis is looking at these ions, you know, and looking at how reactive they are. Do you guys recall the solubility rules for ionic compounds? Does anybody still have those memorized, or did you forget them? Or maybe you never had to memorize them. Unfortunately for Chem 1A, we should have them memorized.
I think I have it back home,
Yeah.
some of
I mean, we could always look it up, but problem is you know, in chemistry, sometimes you look for patterns, and the only way to see these patterns is by repeatedly looking at this stuff over and over again. Did anybody recognize the pattern in the solubility rules? Maybe you didn't recognize the pattern in the solubility rules because you didn't look at it enough.
the lower the charge, the more soluble.
Yeah, the lower the charge, the more soluble. That's kind of the Coulomb's law, you know, electrostatic. But as we get to more complex things, it becomes a little bit. For example, silver. You know, silver is low charge, but why? Is it so reactive? You know, the silver ions, the 115 picometers. The dark spot is the ionic diameter here. The light spot, or the light circle, is the elements diameter. Is this radius or diameter?
Radius is halfway, diameter is full way, so I think it's diameter.
Okay. No, sorry, it is radii.
Oh, no.
Yeah. So double it. Double it for the diameter. What's the biggest atom? Actually, I don't want the ions. I want the atoms.
On the screen it would be cesium at 167.
Yeah.
Or is it not cesium or cesium? Cesium. Thank you.
Do you know the size of atoms? How big are atoms? Just give me a size range for atoms. The small atoms are about what, and the biggest atoms are about what?
5
1 to 6 pico.
Not 1 to 6 picometers. Close. 1 to 6 what? Another unit.
Angstrom?
Angstroms. 1 to 6 angstroms means how many picometers?
It's
100 to 100 to 600. Do you know how I figured that out? 100 to 600 picometers? Because this is the atomic radii in picometers. So we have to double it. And so when we double it, what's the smallest atom? Doubled here.
not any. Helium.
Helium's the smallest. We double it, it's around what?
62.
62. So helium has a diameter of 62. Well, 62 is close enough to 100 because I don't want you to memorize it that precisely. 100 to, what's the biggest?
Cesium.
Yeah, or cesium. Most people call it cesium.
At 596.
Not five, is it 596? Yeah, 596 is close enough to
600.
600. So 100 to 600 picometers, roughly the size of atoms. Now cations are about half the size of the parent. And so if, let's say if lithium, or let's go to sodium. If sodium were 190 double, well, we'll just do the radius. If sodium's radius is 190, then sodium ion is going to be about,
95.
yeah, about half the size. Right? And so let's take a look. These are just rules. These aren't laws. Or these are just kind of general observations. Now look at the dark circle. Does the dark circle look about half?
No. Not for all of them.
Well, not for all of them, but you know, look at sodium. You predicted 95. What do we have?
102.
One close enough, right? And close enough without having to memorize a lot of stuff. So do you see they're all about half? Some are smaller than half, like these transition elements kind of get small. But about half. It's not perfect, right? You look at gold, quite big. Gold is very
Dense.
unique. Okay, what about the anions? Now, the anion is the dark. And so bromide is the dark, bromine is the light. What would you say about the anions? The anions are about
What's that?
twice as big. And so if bromide is 196, then bromine should be about half that. And so let's take a look.
It should be about 98.
Well, bromine comes in at 94. So was that, this is what we do for patterns, right? We look for patterns. We don't try to memorize the observations because there are too many observations to memorize. We look for patterns in those observations and then try to remember those. That makes our life a little bit easier. And so I already know if atoms are between 100 and 600, then ions are going to be between
50 to 300.
Well, it's trickier because these guys shrink. The big ones shrink, and then these guys over here expand. So it's a bit trickier than that. But there are other patterns that you learn. The other patterns is how much does it shrink going across the periodic table. So if you start at 300 here, where do you end up? You end up at less than half, or where? Or if you go to the second period, you start at 167, you end up at 38. So there's quite a bit of shrinkage going across. And so little things like this we look at, rather than when you look at all the numbers, if you look at all the numbers, it's overwhelming. There are too many numbers there, right? And so we look for these kind of patterns. And with these kind of patterns, then you can answer questions that, come out of the blue, sometimes. Since you guys are all students on tests. Not that I put them on there, but, a lot of professors love to put these kind of things on, their tests. So anyway, going back to the solubility rules, let's go back and try to look up the solubility rule. Now, different books will have different solubility rules. Do you want to memorize them one by one? No, so we try to kind of generalize them. And different people will generalize them in different ways. You could buy this, and if you have a photographic memory, you can memorize it or something if you want. But our general patterns aren't going to be perfect. And so I like to use these solubility rules, although they're not always perfect. And then I forgot to go on here. The higher the charge, 2 plus will have twice the force, right? If you have 2 plus and 2 minus, that's going to be 4 times the force, etc. And the distance. And so we look at the charge density, how concentrated the charge is. But let's take a look at the solubility rules. We have 2 sets. The first one's easy. Molecular compound. For molecular compounds, we have the solubility rule like dissolves like.
to severe ulcerative colitis. So I'm taking Zeposia, a once daily.
Is this the one I'm looking for? Maybe not. Can you tell this is older? This is from 1990s.
It's a little grainy.
Do you see what they do with the water molecules? The water molecules look like these little stick twigs.
Yes.
And then there's some methanol in there. But can you really tell? No, they kind of all blend into one another because methanol also hydrogen bonds just like water. And so methanol fits right in here. And so that's what we mean. Whereas oil, like hydrocarbons, even though hydrocarbons have a lot of hydrogen, they're non-polar hydrogens. And so there's a huge difference between methane and methanol in terms of polarity. And so the electronegativity difference is very small, so we call this non-polar. And so methane doesn't fit in there. Methane will just bubble out. Whereas methanol has no problem fitting in. Here. And so methanol is water-like, methane is not. And so this is polar. Not only is it polar, hydrogen bonds. And in fact, this fits in so well, it's called miscible. What does miscible mean?
Infinitely soluble.
Infinitely soluble. And so methanol and water are alike. So much alike that don't drink methanol though. Because if you're thirsty, yeah, definitely do not drink methanol. Well, anyway, that's molecular. So molecular compounds is not that difficult, but the difficult one is remembering the solubility rules for the ionic compounds. So let's talk about the ionic compounds next, and then we'll go on a break here. All right, and so I'd like to look at the cation first. The cation, if it's a group 1 or ammonium. Group 1 are all positive what? Positive charge. Tell me the positive charge on group 1. +1. So kind of low charge, kind of big. On the left side of the periodic table are the biggest atoms, right? On the right side are the smallest. Kind of big. And so not very high charge density. These are all soluble. Okay, if it's not one of these, let's say it's a +2, +3 cation, then it gets more tricky. And so we look at the anion. The first anions that we consider are the nitrates. Nitrate is a -1. It's kind of big. It's got nitrogen with 3 oxygens stuck around it, so it's kind of a big ion. Nitrates. Acetates. What's the acetates formula? Acetates and chlorates. What's the formula for chlorate? ClO3 minus. These are all kind of big, -1. Would you expect them to be very soluble? No, they don't have very strong Coulombic, electrostatic attractions, we'll call them. And so nitrates, acetates, chlorates, all soluble. Then we go to the next ones. Chlorides, chlorides are kind of getting fluorides. Fluorides are, what's bigger, fluoride or chloride?
Fluoride.
Fluoride.
Fluoride's bigger or chloride's bigger? Chloride's bigger. As we go down in the periodic table, things get bigger.
Oh, sorry.
Yeah. So fluoride, why fluoride's missing here? Fluoride's missing because there are too many exceptions. If you have a fluoride, what should you do? If you have a fluoride, you have to look it up in a book. What book should you look for? Or actually, you don't need to look it up in a book, but you could also look it up in the...
You look in the CRC.
You could look in the CRC, good. Or you can look in the...
Oh, you look at index, not index books.
Well, what's the other one? CRC or the Merck index. Those are the big ones. And those are very common. Or you could look it up on Wikipedia. But Wikipedia is there's a lot of opinion on Wikipedia too. And so a lot of people won't accept Wikipedia as a source because it's not a reliable source. But I'll tell you, the chemistry, physical data is pretty good. I look it up on Wikipedia all the time. It's just so convenient. And then thumbing through the Merck, you can't, you know, if you pay for the subscription, sure, then you can search it. But, you know, it's like 2,000 pages. It's a lot of stuff. So chlorides, bromides, iodides are soluble. So like iron 3 chloride should be soluble. Except for which ones? Mercury chloride is not soluble. And silver. And so except for silver is fixed charge to +1. Mercury, it's not both mercuries. It turns out that it's just one of the two mercury. What are the two common charges for mercury?
Hg2 plus Hg2.
Yeah, +1 and +2, but +1 is tricky because it's a 2+. And so this is mercury 1. 1 and 2 are the common charges based on the periodic table. Silver's fixed charge. What else is fixed charge that's neighbors of silver? Gold is variable charge, +1 and +3. Cadmium is fixed charged at +2.
Maybe copper?
Copper is variable charge. Copper 1 and copper 2. And zinc, right. Silver, cadmium, and zinc. Copper variable, silver fixed, gold variable, mercury variable, you know. Palladium variable, nickel variable. Right. What are the two common charges of nickel? Not +1 +2, +2 +3. Everything to the left of copper is +2 +3. Then when you hit copper, it's +1 +2, except for gold, which is +1 +3. And then silver, cadmium, and zinc. And then when you get to gallium, it's +3 +5. And then when you get to germanium, it's +4 +2. Right? Those are the patterns in the periodic table. So silver, lead, and silver, mercury 1, and lead. Not both leads, only lead. What are the common charges for lead? +2 +4, so it's lead 2. Lead 4 chloride is soluble. It's weird. Lead 2 chloride forms an ionic lattice, like sodium chloride. Lead 4 chloride does not form an ionic lattice. Do you know what lead 4 chloride forms? Molecules, yeah. You'd expect them to be tetrahedral. It's molecular. Well, it's got also 4+. How many cations do you know that are 4+? So it's molecular or polyatomic. So chlorides, bromides, iodides. After chlorides, bromides, and iodides, then we go to sulfates. Okay. Sulfate has a formula. And these are soluble, except, okay, silver, lead, mercury. Silver, lead, mercury. I usually do it that way. Okay, silver, lead, mercury. Lead 2, mercury 1, but also mercury 2 and calcium, strontium, and barium. Okay, now silver gets a little asterisk here because silver is, you know, in the, it goes soluble to insoluble, but it passes through what we call slightly soluble. So silver is in the slightly soluble range, which means maybe it'll dissolve, maybe it won't dissolve. Depends on how much. Okay, then we go to what? Not chromates. Those come at the end. Phosphates are at the end too. Hydroxide. Hydroxides are not soluble. Hydroxides are insoluble. So if it's a hydroxide, most likely it's insoluble. Except for which ones? except group 1 and ammonium, which are all soluble. Group 1 and ammonium. And
Calcium, strontium.
calcium, strontium, barium. Okay, 6. After hydroxides, we look for sulfide. What's the charge on sulfide?
It's
2 minus. Sulfides are also insoluble, except
Group 1,
group 1,
ammonium,
ammonium,
and group 2.
and group 2. Good. So magnesium gets thrown in here. So magnesium sulfide is actually soluble, not insoluble. And then as well as calcium, strontium, barium sulfides are also soluble rather than insoluble. Okay, and then the 7th and last one is for phosphates and chromates and one more, and carbonates. Phosphate, high charge, 3 minus. Chromate, 2 minus. Carbonate, 2 minus. These are also insoluble, except group 1, ammonium. If you do group 1 and ammonium first, then I don't have to keep rewriting it each time. And actually, that's it. Just those. And so all the others will be insoluble. So sodium phosphate soluble, but anything else, unless it's group 1, will be insoluble. All right, so that's the solubility rules. We'll take a break right now and then start up again in a little bit. All right, I do have an office half hour today after the afternoon lab, and then a Zoom, or not Zoom, but WebEx. I'll just post a link in Canvas. And then also tomorrow before class, 11 to 11:30, and then after the afternoon class, 3:55 to 4:25. If you have any questions. But I could talk a little bit about the tests too. Let me say one more thing right now and then. Look. Now, solubility and electrolyte are two separate things. We look at them separately, and then we determine the solubility properties of a substance and the electrolyte properties. Now, I told you there are two definitions. One definition is, does it dissociate into ions when it dissolves, or does it stay together, or does it partially dissociate? That's the typical definition. But if you're working with electrical devices, then you don't really care about that definition. The definition that you care about is, does it conduct electricity well, or does it not conduct electricity well? And that's the purely conductivity. So if it conducts electricity well, then we call it a strong electrolyte. If it doesn't, then we call it weak, regardless of what happens. So what can happen is this. You could have a strong electrolyte in the prior definition, or the former definition. You could have a strong electrolyte, but if it has low solubility, then the population, the number, is going to be very small. And therefore it's going to show weak conductivity. And so you could have a strong electrolyte with weak conductivity if the solubility is very low. And so it mixes things up. So it depends on who you're talking to, or whom. If you're talking to a group of electrochemists, then you're talking about just purely the electrical conductivity. But if you're talking to, let's say, the Chem 4, then you're probably talking about the latter definition. And so what we're going to do is we're just going to use the latter definition here, and that is, if it's a strong electrolyte, then it should dissociate near 100% or 100%. And so strong electrolytes dissociate, right? Dissociate completely. Or, well, actually, let's see. Just say about or equal to 100%. So what if it's like 80%? 80% dissociation, we'll probably just call it strong as well. Weak electrolytes, on the other hand, just partially dissociate. When we're talking about partially dissociate, usually we're talking, well, dissociate 1% or less than 1%. And so a lot of these weak electrolytes have very, very limited dissociation, so partially dissociate. I mean, if it's like 30% dissociation, then that's pretty moderate. It's going to conduct electricity still pretty well, as long as it's fairly soluble. And so this partial dissociation is really small, usually, like 1%. And then we have the non-electrolytes. These don't dissociate. So where is water? Would you classify water as a weak electrolyte because it does dissociate? Uh-huh.
If it goes by variable means, if you're talking about distilled water.
Distilled water. Where would you classify distilled water?
As a non-electrolyte.
It does dissociate, right? And so should we call it a weak electrolyte because it partially dissociates?
No, because of the
Yeah, but if you're talking about, if you're talking about the electrical, did it conduct any current?
No.
No. I mean, if we had an ohm meter or, a conductivity meter, then we could actually measure it, and it's pretty much close to zero on that. And so, water, even though it does partially dissociate, the extent of dissociation is so small that water is classified as a non-electrolyte. Yeah. And so some things are a little bit tricky based on that. And so what are the strong electrolytes? What types of compounds are strong electrolytes?
things that would dissociate completely out of
Salts. But we have different kinds. And this is kind of a mix of things, but usually to stay safe, the strong electrolytes are going to be the soluble salts. The insoluble salts, those aren't really going to conduct much, even if they have ions present. And so the soluble salts will conduct electricity strongly. What else? Salts are usually like metal and non-metal. Metals, metals are going to be, but metals are different. Electrolytes are things that will dissolve in water. And so substances that dissolve, metals don't dissolve in water, but they do conduct electricity well. And so some people say, does your drink contain electrolytes? When they're talking about electrolytes, they're talking about the salts that are dissolved in there. So soluble salts.
Ionic compounds.
Ionic compounds are soluble salts, but there are other compounds. These are kind of, they're kind of ionic, but they're kind of molecular. So we term them like polar covalent compounds. Sugars dissolve, but they don't dissociate. So sugars would be non-electrolyte. So non-electrolyte would be like water. Sugars are alcohols, and the alcohols would be like they're polyalcohols, meaning they have many alcohol groups on there, and some have what are called aldehyde groups in there. You have alcohols and aldehydes primarily, but mostly alcohol. Those are sugars, like glucose. And those sugars don't break apart, don't dissociate to any significant extent. Acids, but not all acids, strong acids. Strong acids will dissociate completely, and strong bases. Do you remember the 7 common strong acids? Name them or give me the formula. HCl, called hydrochloric, sulfuric formula. H2SO4. HCl, H2SO4. Phosphoric acid fits into this category, weak.
Acetate.
Phosphoric acid, though, HCl and H2SO4 dissociate about 100%. Phosphoric is borderline. Phosphoric dissociates about 80%, so phosphoric is borderline strong. Maybe throw in the strong, but we'll keep it in the weak. It's about 80%. So when I said 80%, then
What about nitric acid?
nitric acid, yeah. Nitric acid will dissociate about 100%. Hydrobromic, hydroidic, perchloric. Perchloric's formula? HClO4. HClO3. HClO3 is called chloric acid. So these are the 7 common strong acids. Hydrofluoric acid's not here. Hydrofluoric belongs into the weak category. Here. In fact, for the weak electrolytes, actually, soluble stuff. Strong bases. What are the strong bases? Sodium hydroxide. Okay. Sodium hydroxide. Lithium hydroxide.
LiOH. LiOH.
Okay. Potassium hydroxide. Don't remember? Magnesium hydroxide. Strong base, magnesium hydroxide. Iron 3 hydroxide, strong base, iron 3 hydroxide. How about methanol? Is methanol a hydroxide? Methyl hydroxide? Can we call it methyl hydroxide? No, we don't call it methyl hydroxide. We call it methyl alcohol. We don't call it methyl hydroxide. Why not? Because this is not an ionic bond. This is a covalent bond, just a polar covalent bond. This is an ionic bond, right? These are all ionic bonds. So we got sodium ions and hydroxide ions. Methanol is not a strong base. It's an alcohol. It's got a COH. There's a simpler way of saying the strong bases. What are the strong bases? Yeah, the hydroxides, but not all hydroxides are strong bases. Well, let me. This is something Chem 4 people heard before, but we'll repeat it for those who haven't heard before. Sodium hydroxide. A lot of people have this in their kitchen. It also goes by another name. What is it?
Table salt.
Oh, table salt. Yeah. I guess if you ran out of sodium chloride, would you use sodium hydroxide?
It was a
Yeah, the table salt might be in the pantry, but the sodium hydroxide, usually people store under the sink. And so if somebody's, let me go grab some salt, and they're grabbing something from under the sink, you might say, wait a minute, because I might not want that sprinkled on my food, because sodium hydroxide is also known as,
Bleach.
not bleach, sodium hypochlorite
Ammonia.
bleach.
Is it ammonia? Oh, those are the two things I've mixed together.
It's also known as drain
Oh.
cleaner. Drain cleaner goes by the name lye.
Right.
And so I remember, you know, a popular brand of drain cleaner is this Red Devil lye. Have you heard that? It's been years since I saw it. I've gotten it before, but I went in there and now they don't have Red Devil lye, but it's another one with a devil. And it's got red devil on it. A red devil image, but not red devil. It's